Good morning, everyone, and welcome back to Foundations of Algorithms for Week 8. We've got some really exciting content for you today, and so I hope you're all awake and lively to hear about some new things. We have one of my favorite figures in computer science history today. This is Douglas Engelbart, who was born in 1925. And did any of you have like a kindergarten boyfriend or girlfriend who you just like played around with? Yeah, a couple people here. So one of my very early primary school girlfriends, her grandfather was Douglas Engelbart, and we got married on the playground, so I guess he's my grandfather-in-law. But Douglas Engelbart is known as the founder of human-computer interaction, which is the field that asks, okay, so we have these complicated digital devices, but how do we design them to actually be usable for people of all different sorts? How do we design interfaces that actually make them accessible? For example, if everyone knows that if you see a red X, it means close. But that wasn't an inherent part of the design language of computers when they started up. It was just a terminal and a keyboard. So Douglas Engelbart came up with the notion of designing computers in a way that becomes intuitive for people. So he was the inventor of the computer mouse and of the idea of having different windows on the computer. And so he was actually foundational for the computers that we use today. Not just the algorithms, but also the interfaces. And he presented many of the ideas of what became modern computers in an event known as the Mother of All Demos. And you can go back online and actually watch this demo, and it's amazing how prescient he was about what the future of computing would actually look like. And so there is a little fun story that I think is my personal connection to one of these figures. But you know, I was thinking that we need to take FOA to the next level. So I wanted to invite a slightly higher profile guest to this lecture. And I can tell you for the next couple of lectures, she might feature a little bit. So I called her up and I said, hi, are you busy? I know you've come off your tour, but I've got some students who want to meet you. And this is what she said. She rejected me, unfortunately, but we can still chase after her concert tickets at least, and that's going to be some of the theme for the next couple of lectures. So did anyone make it to the Eras tour? 1, 2, come on. So I actually took some of my FOA staff to the Eras tour a couple of years ago, and this is going to be our problem for the next couple of lectures. So for those of you who remember trying to get tickets, the website crashed, didn't work very well, and so we're going to think about the algorithms that can actually be used to do ticketing, to manage the seating, to analyze the music, and this is something that I'm very excited about. So if you'll go way back when, the very first part of going was, of course, starting with the ticket office. Now, in this case, we've got a virtual ticket office. So does someone want to tell me, what would be the right way to do this fairly, to distribute tickets? And given that KJ actually attended, we'll get her opinion on the fair way to distribute Taylor Swift tickets.
So in an ideal world, I think you would have a queue of people in one line and each person would get one ticket, and we could keep moving further down the line, giving one ticket to a person until we ran out of tickets or out of people.
And what actually happened?
People who buy up bulk tickets and then resell them for really, really high prices. Whatever.
So probably what is considered to be the fairest way to allocate tickets is, as KJ said, first come, first serve. Now we have a couple of data structures that we could potentially use to represent this, and KJ mentioned the word queue, which seems to be the right kind of analog. We know how a queue works in real life. Okay, Vicky, how should we implement a queue with our data structures? What data structure should we pick?
Array.
An array. An array is not a bad idea to use for our queue. So let's try out option 1. So I'm going to need a couple of volunteers who really want to come to the end of semester concert. Okay, so right now this doesn't look like you're particularly eager to get tickets. That looks a bit better. Okay. Here is our array. We have position 0, position 1, position 2, position 3. So, Vicky, you've still got the microphone? So tell me how I should make this work. Which index in the array should I give a ticket to? To whom should I give a ticket? Like, I've got a ticket. Who should I give it to? Okay, which is at array index 0. Okay, so I give the ticket to Jen. And now what do I do? I've still got more tickets. Okay.
But I want to bring a friend.
You want to bring a friend?
Yeah.
Okay, so maybe we'll give a second ticket to Jen as well. So one thing we can do is we can go across like this, and Lily gets a ticket, and Devansh gets a ticket. And remind me your name?
Marvel.
Marvel gets a ticket as well. But now let's imagine that we have new people who are joining the line. So let's say that Oscar comes along and wants to come to the concert as well. But Jen doesn't want to stick around just because Oscar wants to join the line. So Jen wants to leave, right? So Oscar doesn't join the line yet. Jen, you can go home. Don't step forward yet. Stay there, Jen. You can go home, or go to the side for the minute. Okay, now which array index should I give it to? Where should we put Oscar? Well, if we put Oscar in index 0, then what happens when Oscar just jumped the line? That doesn't seem very fair. Okay, let's rewind that. Oscar, go back. Jen, come back here. Okay, we've just given Jen her ticket, and she wants to leave now. So what should we do?
Everyone step forward.
Okay, so Jen is at index 0, and she leaves. So how do we do that in C? What would we have to do? To put what is in index 1 into index 0, what would we do? Remember the flasks that we had earlier in semester? We could do a copy, right? So we can copy her. Okay, copied, and now we can copy Devansh, and now we can copy Marvel, and now where do we put Oscar? At the last position. Okay. So now Lily wants to get her ticket and leave, right? And now what do we do? Okay, there's a copy, there's a copy, there's a copy. So for every person who we get to the front of the queue, how many copies do we do?
For every person.
Let's say we have an array of length n.
N to the power of 2.
N to the power of 2? For each person. So if one person leaves, how many copies do we have to do?
4.
If there are n places.
N minus 1.
Yeah, n minus 1, which is big O of?
N.
Yeah. Every time we delete someone from the front, we have to do n copies. Now, this doesn't seem like a very efficient data structures way of doing this whole operation, does it? Like copying everyone every time we want to do a new ticket. Okay, so we need a new data structure. So I'll keep all of you here. So how many steps did it take to insert Oscar once everyone had moved forward? When someone new came to the line, how many steps did it take? How many copies did we have to do?
And when Oscar come to the first one?
Yeah. When Oscar joins. Okay, Oscar join, how many steps did that take? Yeah, Jen's right. It only took one step. There were no copies, nothing extra. He just joined the end of the line. So if we were keeping track where the end of the line was, all we do is put him into place there. So our insert at end is big O of 1. It only takes one step. And push, which was our operation to put something in at the front of the line, how long would that take? If we wanted to instead Oscar leave, now let's say we want Oscar to cut the queue, how many copies would we have to do if Oscar was going to move into first place?
1.
1? Okay, Oscar, try and go into first place. This isn't going to work. Devansh is already there. So if we want to preserve Devansh and not wipe him out from existence, what would we have to do?
Remove him.
Well, we don't want to remove him. He's in line. He's been waiting here. But if Oscar wants to cut, what we could do is move everyone back a place. And the way we'll do that is Marvel will copy you back one position. Devansh will copy you back one position. And then we put Oscar in at the front. So that takes O of n as well. So we've got our insert at front, or our push operation is what we'll call it, takes big O of n. Our remove from the front is also going to take O of n, and it's only our remove at the end that's going to take O of 1. And this doesn't seem like ideally what we want for our queue. This is going to take a lot of work. So instead, we've got a fun demo. So everyone back. Go wherever you want, off to the side. And I need a police person. Okay, so now we've got a new data structure, and Lily has a pointer that can point to anyone else in who wants to be in line. So let's say we want to add someone to our line to see Jacob Collier or Taylor Swift. What can we do?
So let's say I want to have.
Got to use the microphone.
Oh, let's say I want to add like Devansh to the line.
Yep.
Devansh, you can come up. I'll first I'll try attaching Devansh, who's probably the next person, or let's call him the next person. I'll attach the pointer from Lily, right?
Yep.
From Lily to Devansh.
And make sure to hold the microphone high or it's not going to catch. Okay, now let's say Jen comes along and also wants a ticket.
So interesting one. Oh, first things first, because Devansh has a pointer which I'll probably call N. Can I do that?
Well, we've got to start at the front of the line, right? So what can we do?
I think we have to probably like iterate through from Lily to Devansh.
Got to hold the microphone to your voice.
From Lily to Devansh, and then I attach.
Okay, so from Lily, what do I do?
Iterate to the next one, which is through the point.
Okay, so I'll follow Lily's pointer. Okay, I'm at Devansh now.
Yep. And then I know that the next one is, doesn't exist, so I know that that's where I need to attach to.
So I've got Jen, and Jen has an address, and so we can link her up.
Yes.
Okay. That looks reasonable. Okay, looks good. Now let's say that Lily wants to leave.
So
Lily, try leaving.
just setting. Oh, that's not very good.
This is not going very well. Okay, come back. Obviously, we need a better strategy.
We could try. Firstly, we tried difficult.
Is it? You can.
You can just free up the.
Like, what if Lily passes something to her? If Lily passes what she's holding to Devansh.
Well, then Devansh is holding 2 pointers, which he probably doesn't need.
So like then we remove what I already have, like we remove this red cable here, like what connected me already.
Okay, so let's take this a little slower. So maybe let's do the first thing. Okay, first thing we need to do is find out who's going to be the new head of the line, which was a good insight from Jen. So how do we find out who's going to be the new head of the line if we want to remove the first person?
The next one.
Okay, so follow the cable along. Okay, I've got the new person who'll be at the head of the line, and now what can Lily do?
Just unplug and just.
Okay, there we go. Now let's say Oscar wants to join.
So we go through. So we know that Devansh is at the beginning,
Yeah.
and so we move over to the next person on the list.
Okay, follow along. Devansh, do you want to still hold your pointer?
Can we move to the next person after Jen? Is there anyone else?
No.
No. So then we attach Oscar to Jen.
Okay, now what happens if Oscar has a change of heart?
Then
I can unplug him.
yes, I don't really know who is the at the very end.
Well, let's say we don't know where Oscar is. How can we find Oscar?
We have to go through Devansh.
Okay, so let's start at the start of the line. Are you Oscar? Okay.
No, I'm not.
Are you sure?
Yeah.
Okay. Are you Oscar?
Yes.
Okay, you can leave.
Okay.
There we go. So that worked pretty easily. Now come back. We'll reset that. And now let's add Marvel. So how do we add Marvel?
We go through Devansh first.
Okay, start at the head of the line.
And we go through
Go through again. Okay.
the next one. We go to Oscar.
Okay, do I go through again?
We check that if the next one's empty.
Okay, it looks pretty empty.
So we can add Marvel to the end then.
Okay, there you go. Do you want to join up? Now let's all just shuffle along in physical space a little so we have some more room.
Did I notice?
Yeah, you can remove that. And Oscar still isn't a big fan of us, nor of Taylor Swift, and he still wants to leave. So now how do we remove Oscar?
So first we go through the list.
Well, first we have to find Oscar. Okay. Are you Oscar? Are you Oscar? Okay, let's see. Do the next iteration. Are you Oscar?
Yes.
Okay.
And then we unplug both Oscar and Marvel. So we first unplug Oscar and then we go in through Oscar to never mind, Oscar's on.
Oh, but you just deleted that. I don't know who's next anymore. Okay, replug it. We've destroyed this list.
Unplug the link between Jen and Oscar.
Okay. Okay, well, we'll reverse that. That didn't work either.
Just the one between Jen and Oscar. We keep track of Oscar for now. We just want to unplug the link in the very end, between the item before Oscar.
So instead of keeping track of Oscar, who are the people we need to keep track of at this point?
Not the people in between, right after and right before Oscar.
Yeah, so let's keep track of Jen and Marvel. And then what will we do?
Yeah,
Jen, you can say that a bit louder so that it catches at least in one of the microphones.
Connect my plug to Marvel's plug.
Yep, to Marvel's plug.
Sorry. Remember go.
Yeah, this way.
Sorry.
There you go. And now what do we do with Oscar's link?
He's gone.
Oscar's gone. So now we can get rid of Oscar. And so when we have this link in the middle, we have to do a little more bookkeeping to make sure that we're keeping track of everything fine. And this is our new data structure. You can see that the operations were a little different to the linked list. So let's go through those operations one more time and figure out how long they took in terms of the number of steps. It didn't look like we were doing many copies. We weren't doing this like, okay, you move along, now you move along, now you move along, now you move along thing. So let's go through the operations again. So if I wanted to remove the person at the front, how many steps did that take?
One.
Just one step. I'd go along to the next person and then we'd just forget the first. Okay, what about adding someone to the end?
Because we have to go through everyone. I think that'll just be just n, just O n. So we have to go through the entire list.
Got to say it in the microphone.
We have to go through the entire list, so that will be O n.
Okay, O of n normally. Can you think about a way that we could make that much faster?
We could have an n pointer pointing to the very end.
Yep, so we could keep track of the tail. We'll call this the head, and we'll call that the tail. And if we know where the tail is, how many steps will it take us?
1.
Only take us 1 step to add to the end. So that seems pretty good. What about to find something? If we wanted to find where Oscar is?
We'd have to go through the entire list, so divide.
Yeah, so we have to start at the start and keep following the link. So you Oscar, or you Oscar, or you Oscar, or you Oscar. And in the worst case, that will take us how many steps, everyone? N steps. So O of n to do our search. What about our deletion?
That would, because we have to go find the person, so it's kind of similar to the search.
Yep.
Go over.
So to delete Oscar from an arbitrary place in there, we had to find Oscar, which meant that that was O of n. And am I forgetting any operations?
Insertion.
Oh, insertion at an arbitrary location. So if I wanted to put someone in the middle,
Same thing.
same thing again, because I'd have to find, let's say I want to put someone before Oscar but after Jen, then I would still need to find Oscar as well. So that's also going to take O of n. So we have a very different set of properties than the array. For the array, to insert someone at the front would take O of n, whereas here it just takes O of 1, because in the array we had to copy everyone over to make that first slot free. Likewise, to remove someone from the front in an array took O of n steps as well, because when we removed the person from the front, we had to move everyone else forward 1 step. So linked lists turn out to be a really efficient way of implementing what we call our queue. Now you can do a queue with either an array or a linked list, but the properties you get are pretty different in terms of the algorithmic efficiency. So with that, can we have a round of applause for our Taylor Swift fans and our Jacob Collier fan? And we'll keep going on. This quite clearly motivates for us why we'd want to use linked lists, and also why we're going to have bothered with this whole dynamic memory thing that we were talking about. Because dynamic memory is going to be the thing that allows us to arbitrarily add and remove links as we need and use these pointers in order to ascertain how we can link things together. So in C, this looks fairly straightforward. You might think, well, that looked a bit complicated, but the code for it is really not that hard. At its core, all we need is a struct that keeps the idea of what a node is. And in this case, our node had data, which was the name of the person, but along with that, they also had a link to someone else in the structure. And this link we will call next. Now you'll notice here that I've defined 2 type aliases here. Now this type def word, you don't need it to necessarily to make a struct, but it's helpful because it allows you to call a variable type that you use multiple places throughout the code, something else. So instead of having to write struct node everywhere in the code, if I use this type def, every time I want to use struct node, I can just write node t instead. Likewise, I could have a type def for a data type. It could be an int, it could be a float, it could be a double, but instead I've chosen to alias it to data underscore t, so that if I want to change my code to work with floats and it was only working with ints, all I have to do is change that one type alias. And then inside my node, not only do I have the data, but I have the pointer to another node. Now, in C, you have this challenging problem because how does the compiler know what a node t is while it's still inside the definition of the node itself? So C reads source files top to bottom, and this is just like when you create a function, you need to have a function prototype if you're going to use the function before you've actually written all the code higher in the file. You can also do this with types, and in particular with structs. So the fact that we have our type def for our node t is what allows us to use the node t within the node, because C says, okay, I know when I see the word node t, it's a type, and so I can put the logic together in such a way as to know that because the user's told me ahead of time what to expect, when it later comes, I'll be able to refer back. And so this is all we really need to get started with actually writing our code. So now let's look at a few examples that are very similar to what we were just doing of how to actually write some of this code in C. As usual, we're going to point out a few of the features of the code as well as looking at the specific algorithm itself. So the first feature I want us to look at is this interesting hash define at the top. Now this is a little different from our prior hash defines. Now remember, a hash define is just like a find and replace operation in that it's finding and replacing the text of a function. So in this case, every time in my code that the words insert at end is written, it's going to replace it with insert at index. And what it's going to do is a little bit more sophisticated than the standard hash defines we're used to, because it's going to substitute appropriately in X and Y for whatever the user has written X and Y elsewhere in the code. So if it's insert at end variable 1, variable 2, that'll be replaced with insert at index variable 1, variable 2, list length variable 2. So X and Y are going to get substituted there. And you can see what this is actually doing. This is saying, well, inserting at the end of the list is the same as inserting something at an arbitrary position at the list where the arbitrary position that you've chosen is equal to the full length of the list. And we know in C that it's going to evaluate list length first. So what this will first do is it will take the list, go to the end, figure out how long it is, and then do insert at end. So how many operations will this take us in terms of n to do this? The way I've written it. So how long does list length take? How long does it take to find out how many items are in the list? It takes n steps because we have to go through all n things. We have to count 1, 2, 3, 4, 5, 6, 7, 8 following the links. And so once we've done that, all we've done is figure out what that index is that should be list length. And then to insert at index, it's going to take a further n steps, because now we know that, let's say the list is length 8, we're going to start at the first one and go 8 steps forward again. So this is actually not the most efficient way of, it is far from the most efficient way of writing insert at end, but is useful to illustrate our point here. Now, here we've defined a custom type, named, which is a character array that fits up to 20 characters. And then we've defined a second type alias defined from that first type alias, which says whatever data t is should be a name. Then we have our nodes that we're going to use for our linked lists, and these just represent the people that we had at each stage, so where each person had some data associated with them and a pointer to the next one. And now we're ready to look at the actual algorithms. So we have a few functions here. We have print list, which is going to go through the entire list, printing each person by person. Push, which is going to be our term for inserting someone at the very front. List length, to calculate how long the list is, and insert at index, which will insert at a given index. And then our last one, pop, which is taking the first person, getting whatever it is, getting whatever data they had, and then removing them from the list. So let's first look at our main function and see just generally what we're doing. We're going to create an initial node, and we're going to call this the head node. Remember, head is the first one, tail is the last one. And we're going to actually use a pointer to a node in this case. And we'll use our function from last week, malloc, to ensure that we have set aside the memory that we need for a full node. Now you'll notice here that I didn't include a typecast to a node t star. And there's actually a dispute in the C programming community whether it's a better idea to explicitly include this typecast so that future programmers can clearly see what you're doing, or whether it's better not to do it. And I'm happy to talk a bit more about that outside of class, but malloc doesn't actually return on its own a node t star. What it returns is what we call a void star. It is just a pointer to a block of memory, doesn't really matter what's in that memory, and then it's up to you to choose how you want to use it. So you can tell it how much memory to put aside, and in this case, we're telling it to put aside as much memory as a node t takes up. And then afterwards, we're just saying, okay, use that blank memory, and we're going to use that blank memory as if it was a block of memory corresponding to a node t type. Now, once we've been given that block of memory, there's nothing in it yet. And so we have to be very careful to actually initialize the variable. It's not necessarily set to 0. It could be whatever random junk was in the computer's memory before. Now, a kind of a warning point here is that depending on the particular configuration of your compiler and your computer settings, or just luck, it might be set to 0. And you can get bugs in your program that seem to not be there all the time, because when you run the program on one computer, that computer happens to set it to 0, so things work as you expect. And then on another computer, it's just putting in random junk in there, so it might not work. And this can create what's called a Heisenberg bug, where it's there only when you're not looking at it, and then as soon as you try and debug it, you've changed things in the environment a little, and so the bug appears to disappear. So is the bug really dead or alive? We don't know. So first, what we're going to do here, after we've done malloc, is just assert that malloc was successful. If malloc is unsuccessful, it'll return a 0, a null pointer. And so by asserting head, that's equivalent to just asserting that head is non-zero, which means that malloc succeeded. Then what we're going to do is we're going to set the pointer of the first person to null. We're going to set it to 0 because when we only have one person in line, there's no second person in line to point to. And if we don't explicitly set that, just like I said a second ago, it could be random junk. So it could point to some address, who knows where. So we need to set it to null so that we're sure that we haven't accidentally left that pointing to somewhere in the middle of nowhere. And then in this case, because I am using a character array as my data t type, I'm going to copy in the string nick into the data, the element of the struct called data. Now, we haven't really talked much about string copy. It's going to go through the source string and the destination location, and character by character, copy the character it sees at the source to the destination until it finds a null byte. Now remember, this is a different null. This is null with one L as opposed to a null pointer with two L's. And then we're just going to insert some things to our list one by one. Print the length of the list, print the head of the list. We're going to remove the first element from the head of the list, print the list again, pop the second node off the head of the list, print the list again. Okay, so before we actually look at the linked list algorithms, I want to just give this a test, run it with the main function, and observe the output. So the first thing we do is construct our list, Nick, Jung, Nash, Flow, Rose, min, 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 min. Then I have removed the first element, and I get Jung, Nash, Flow, Rose, min, min, min. And then I remove another one, and I get Nash, Flow, Rose, min, min, min. So it's operating as we would expect, as removing someone from the front of the line, giving them their ticket, and then moving to the next person. And in this case, it's printed min, min, min 3 times. It's printed min 3 times, but these aren't the same min. These are different nodes. So even though the string looks the same, it's not actually at the same location in memory. These are 3 different nodes within our linked list that all just have data that looks identical. But if you were to compare the nodes, they wouldn't be equal because they're at different locations in memory. They've got different pointers, even though the data that they have inside of them is represented the same way when it comes to the data t element. So let's look at our different functions. So insert at index is going to create a new pointer for our new node. We have a variable I that's going to keep track of where we are in the list so far. And then we're going to create a new node like we did before. Whatever was the first argument is the stuff, the data that we're actually going to fill it with. So let's do a string copy. So put that stuff in the new node. And let's start it off by not pointing to anything. So first thing we do is check if the place that we're trying to insert it is the first index. If we are trying to insert it in the first index, then all we do, so this is equivalent to putting Oscar at the very start of the line and having him jump. What we do is we attach Oscar's link to what was previously the head of the line, and then we just update things so that we remember that Oscar is the new head of the line. So instead of starting at whoever was here before, we now start at Oscar. Oscar is joined up to the prior head, and then we can go from there. So that's our easiest case. Set Oscar's pointer, his next to be the prior head, and then just return Oscar, or return a pointer to Oscar, because Oscar is our new head. And so our function here is going to return whatever the head of the line is. What if he's not first? So if we insert him to some arbitrary place, then what we're going to do is we're going to follow the links using this for loop, and we're going to increment I to keep track of how many loops were followed so far until we get to the position we want to be at. Once we're at the position that we want to be at, and follow him to the position we want to be at. The way we do this is we keep track of the current node. So you can think of P as the current node that we're looking at. And what we do is we say, okay, figure out what the current node is pointing to. Whatever it's pointing to, that'll be our new current node. So get P.next, P dash arrow next, follow it along. Okay, it's that. And now P will be this thing. Okay, figure out what P next is. Okay, follow it. Now this is our P. And do that until you've done that I times to get to the ith position. When you're finally gotten to that point, now we attach Oscar. And the way we do that is we say, whatever Oscar's next one is, should be whatever the current one's next one was. And then instead, we'll jump Oscar in. So now the prior one now points to Oscar, and Oscar points to the one that was previously next. So I will draw that out for you really quickly. So what we're going to do is, this is Oscar, or we'll call him new in this case to keep our terminology consistent. This is our new one. And we're going to say, well, new's next one should be whatever P's next one was. And then P's next one should instead be that. And then we cross out that line, and now new has been put in the middle over there. And that's exactly what this code is doing. It says the new's next one should be previously what was P's next one, and then P's next one should now just be new. So put new in the middle of those two. And then return P. Okay, what about push? Push was put someone at the front of the line. That was really easy. So that's equivalent to our case where we inserted at index 0. Print list, very simple. We do the same thing we did before with iterating through the list until we get to the end. But in this case, you'll notice that we check actually, let me see if there was a bug in this code. There is actually a bug here. Does anyone know what the bug is? What happens if the index that I am looking for is not within the bounds of the list? Probably get a seg fault, because I will get to a place where I have a null pointer, and then I will set that null pointer to be my current one, and then when I try and dereference it, I'll get a seg fault. So this could be written a bit more defensively. So let's look at print list, and this uses a slightly different syntax to achieve the same thing. There are a bunch of different ways of writing this code, and that's one of the things that makes code kind of fun. So in this case, take the head in. And what we're now doing is we're saying while the current thing that we're looking at, while the pointer that we're looking at is not 0, so that means it's not a null pointer, which means we should be able to dereference it. So while it's not null, print whatever is at its data. And in this case, we're doing string type, so we're using the %s sign. And then do the same thing where we say, okay, the current one is p. Look at what p next is, and then that becomes the new p. And do that as long as p actually is a non-zero value. And list length is very similar, except this time we're keeping track of a counter at the same time. Okay, let's look at an example of me doing this wrong. Okay, let's take a look at, close that. In this case, I've made only a very slight modification to my push. And I'm going to run it and show you what happens. And then we'll try and find the bug. It's called bad push pop. So it prints Nick, and then it says assertion P failed, aborted, core dumped. And these are the kinds of messages you might get when trying to write your own linked list code if you mess up. So let's go through it. First thing I did was exactly before, I made a new head, and then I pushed Jung to the head. Now let's look at what push does. Push creates a new node, mallocs it, asserts that malloc succeeded, copies the data in, and then points news next pointer to what was previously P, which was previously the head, so we could write that as head, and then returns the new element that just created. It should be the new head. So my question is, what is the bug? I'll give you a minute to look at that. What is the bug? Okay, let's walk through it together. So what does the push function return at the end?
Is it new?
Yep, it says it over here. And our new is our new node we just created. And in the case of like inserting someone at the front of the line, what is new?
The person who was like second before the first.
Well, let's take a look and see carefully. Okay, new created a new node, and then new's next pointer is what used to be at the start of the line. And so if new next is the old start of the line, what is new? New next is the old start, so what's new? It is the new start. So new should be the new start of the line, but let's look back at our main function. When we called push, and push returned the new start of the line, did we do anything with it?
No.
No, so that means when we pushed Jung, the new head of the line hasn't been updated. So we probably have to do something like this to actually take advantage of the fact that push is telling us what the new start of the line is. So that should at least make some of our difference. So let's recompile it and see if we've fixed it. There we go. So all that we were missing was making sure that we had actually updated in our main function what the head was. Now, the example code that we're going to give you to use for a lot of the rest of the semester knows that this is tricky to like remember all of these little small pieces. And so what we can actually do is we can have another structure that saves what the head of our linked list is, and we can call that a list T, so that you don't have to worry about the updating yourself. The list T structure can do that. And we can have code that hides that away from the user and performs another level of abstraction. So we can have our node T that represents a given node, and we can have our list T that represents our list. And our list T can keep track of the head. If we wanted to, like we discussed before, it could keep track of the tail so that we can do inserted end very quickly. And this can be another effective defensive programming technique. So if we open better pushpop.c, you can see that's exactly what we've done here. And you can download these examples after. In last lecture, we would have mentioned that every time that you do malloc, you're asking the computer to give you some memory. And if you keep doing that, your computer only has a limited amount of memory. And if you ask it for memory, fill it up so that the operating system can't just kind of pretend to allocate it, and then you don't free it later, you can get what's called a memory leak. And if any of you have seen your computer slow down after leaving Chrome running for too long, you might have actually experienced this. Chrome is a really complicated piece of software, and it's hard for the people who write it to keep track of every time that they have allocated memory. And so what you get is something called a memory leak, where there's memory that's not actually being used. It should have been freed, but isn't. And over time, if you keep running a program that has a memory leak, the memory used by that program can keep growing and growing and growing until your computer runs out of available RAM or available temporary memory to actually run efficiently. What it will do at that point is something called swapping. So it takes whatever is in the RAM, writes it to the hard drive, and then puts the new thing in the RAM, and then when it needs the old thing that's on the hard drive, it swaps it back and forth and back and forth and back and forth and back and forth. But reading from the hard drive is multiple orders of magnitude slower than reading from the RAM, and so your computer slows down many, many times, or many orders of magnitude, because it's having to continuously swap things in and out of memory in order to deal with the fact that one of the programs didn't use free. And so what I'm going to show in this demo is an example of a memory leak, which is pretty common when using a dynamic data structure that uses malloc and that allows for insertions and removals as you go. And this is an example of a memory leak and how to detect it. So first, let's find the memory leak. So let's look through here. I have my pop and push functions kind of as before. Only this time, instead of having a name T that is an array, this time it is a pointer to a block of memory that will contain characters, it's still a string, only this time the way we're going to make the string is by using malloc. So let's look at the way that we're creating a new node. What we're doing is we're mallocing the node itself, asserting that malloc succeeded, and then to fill it with data, we're going to do something a little more complicated. To fill in data, the first thing we want to do, because data is just a pointer to a block of memory that's going to contain some characters, we have to allocate that memory. So we run malloc, and how much memory do we allocate? The size of a char, so on most computers that's going to be 1, multiplied by the length of stuff that we want to put in the element, plus 1 for that null byte. So we have allocated enough memory to contain the string that we're about to copy into it. Then we run string copy it in, set its next pointer to be null, and then do the same insertion as before. So the additional step here was, along with mallocing memory for the node, allocating memory for the node, we're also allocating memory for the data that's going to be stored inside. Well, we're going to be allocating extra memory for the data pointed to by the pointer inside the node that points to the string. So we have the node. Inside the node we have a pointer. And that pointer needs to point to some allocated memory. So this step is just allocating that memory, taking its address, and putting that address inside the node. So I will do a very quick visual diagram just so you can see what's going on there. So the first thing we do is allocate a chunk of memory for our node T. And this will be random stuff, so we've got to fill it up. So the first thing we're going to do is create a pointer data T, and that is going to point to another chunk of memory that is going to be our name. So data T, remember, we used a type def to make this really a char star. And so a char star needs to point to a block of memory containing characters. But because we're doing this dynamically, we've actually malloced this. And then this is also a pointer. That's our next pointer. And the reason we're not allocating something for that is because we allocated that in a previous step. That was another node T that we allocated at some other time in our program. And so all we have to do is join it to that pre-existing node T. But remember our rule. For every time we allocate something, when we remove it, when we're no longer using it, we need to free it. So let's go through our code to make sure that we've actually freed things. So this was our addition step, same as before. Our push is the same. But let's look at free list, the way we get rid of the list when we're done using it. So the way this is written is it starts with the head. So we could write head there in theory, but then we'd need to also do. So that's another way of writing this, which is perfectly legitimate. So starting with the head, what we're going to do is we're going to say the old node is the one we're currently looking at, move to the next one, and then free that old one. We don't need it anymore. The reason why we have to keep track of the old one is because we need to free it. So we can't just go delete, 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 because if you delete it without moving to the next one, then you've lost that pointer, so you don't know where to go. And if you move to the next one without keeping track of the one you just came from, then you won't be able to free it. So in this case, what we've done is we look at the current one, we move to the next, still keeping track of it, then we can free the old one, then we move to the next, keeping track of that one, we can free that, and we do that and go through the whole list. And we should be done. We should have no memory leaks, right? So in theory, we think we've matched our mallocs with our frees, so we should be okay. What have I missed? Let's look over here. For every node that I create, how many mallocs do I have? Do I have 10? Do I have 0? Do I have 1? Do I have 2? Okay, so those of you who said yes to 2 were correct. And the reason is as follows. If you take a look at what we were doing to create our node T's, not only did we have a malloc here, but we had another malloc here because we were mallocing not only the memory to contain the fields for the node T, but we were also mallocing the memory for the string, the name of the person that we were storing inside the node. And if you look at what our code was doing, our code is only freeing the node T itself. And freeing the node T is only going to free this block. It's not going to free this block. And so we're going to have leftovers where the computer has allocated for us lots of these name T's, but when we're not going to have told it that it can free them. And so they're just going to stick around and we'll get a memory leak and our program will be as badly behaved as Google Chrome. So unfortunately, it becomes quite tricky as a developer to keep track of all the mallocs and all the frees that you've done and make sure you've paired them up. We have a few approaches to dealing with that. The one we're about to see is using tools that specially intercept the stuff that your program is doing, monitor it, and attempt to catch every time you use a malloc and every time you use a free and match them up to see where you might have missed. So let's run some of those tools now. I have at the top of this, I have a guide to which tools you can use depending which operating system you're on. And Mac OS has in recent years been quite finicky at this, and so that you've had to use a custom tool on Mac as opposed to a tool on as opposed to a specific tool on Linux. So let's first compile this. It's called badstring.c. So it actually runs fine. Just like Google Chrome runs, it doesn't crash, but can still take up all your system memory. So we have to use one of these tools in order to sometimes even know that there's a problem or watch our computer slow down. So let's run the leaks program because let's run Valgrind. And then Valgrind takes these arguments. Oh, bad string. And you can see it runs this program and prints out a lot of output. And let's look at what its output was. So first it tells us the normal stuff that the program output, and then when the program finishes, and when Valgrind finishes, it gives us a summary of what happened in the heap. Remember, when we do memory allocations using malloc, that's going to instruct the computer to use the heap to give us the memory and not the stack. And so it says it's allocated 24 bytes in 5 blocks. And let's look at how many names we created. We did 5 names, so 24 bytes seems right. So that's 4, 8, 12, 13, 14, 15, 16, 17, 18, 19. Why do we have some extra bytes? Anyone? Why do we have some extra bytes? Why does a string take up 1 extra byte each time you make it? Null byte. So 19 plus 5, that's exactly right, 24 bytes in 5 blocks. But if you look how many mallocs there were 11 and only 6 frees. So we have a gap of 5. It's pointing out that these numbers don't match up, which means that we have all of these leaks. And then it goes through each of the individual leaks that it found. So right now, this doesn't give us enough information because it doesn't really tell us exactly where, but it does say that it happened inside the main function, and inside the main function in inserted index, and in inserted index at malloc. Now, in order to get more information from it, we can actually pass the compiler an additional option, which is -g. And what -g does is inside the program that the compiler spits out, it's actually going to include a copy of the source code as well. And this means the tools that you run can see not only the code of the program that is compiled, but it can see the original source code as well and sometimes match those up. So you sometimes are going to want to add the -g flag to allow your debugger or your Valgrind tool or your leaks tool to actually give you the information, and so it can point back to, oh, it's exactly this line of the code that the problem happened at. So let's run that and run Valgrind again. And now if you look, it says it happened at insert at index line 76, which was called from the main function at line 51. And this is telling us where the original allocation that was never freed was. It's not telling us where the missing free is because it doesn't know where that free should be. All it can tell us is where the original allocation happened. So let's look at badstring.c in line, where was it? Inserted index line 76. So let's go to line 76. What's at line 76? Ah, it's the malloc of the memory for the names. So what this is telling us is that the things that we're missing a free for are the mallocs that were used on line 76 over and over, which was to make room for the names in memory. So these tools are quite powerful to allow you to figure out what's going wrong in your code. So now what we should actually do is see what the correction is. So let's open betterstring.c. And this is the same thing, only now let's look at our, where is it? Our free list. And now our free list has an extra line in here where we free the data, which is this name, before we free the node itself. And so this is now adding that extra free in there. So if we compile this, clang-g, betterstring.c. Oh, need my -o flag. Now I do Valgrind, betterstring. There you go. Heap summary, in use at exit, 0 bytes and 0 blocks. So that means we successfully freed everything that we allocated. Total heap usage, now our allocations and our frees are matched up. All heap blocks were freed, no leaks are possible. So we're pretty happy at this point. So now let's take a 10-minute break, and then we will come back at 10:30 to continue on with our linked lists. Welcome back, everyone. So to refresh our memory about where we were, let's remember our insert at end function. Our insert at end function, remember, was to figure out how long the list is, go to the end of the list, and put someone at the end of the list by attaching them there. How long did that take in big O time? Who said? Say it again. O of n? That's right. It took us O of n. And that's because we first had to figure out the length of the list, which, did we really need to figure out the length of the list a priori and then do inserted index? Do we need to do that? No, what we can just do is we can go through, get to the last one, and attach something to the end without first calculating the length. But this was inefficient, so what was our workaround for making this much faster? We can have a pointer to the tail. So now this is getting a little bit more complicated. We've got all this bookkeeping because we need to keep track of which allocations we've done, we need to keep track of which allocations we've done, we need to keep track of the head, we need to keep track of the tail. Every time we run push and pop, we need to update the head and the tail. So this is getting very bookkeeping-y very fast, which is a feature of data structures, but maybe there's a way we can abstract this out. And that's what I mentioned before, that we can actually write some code to make it a little bit easier for our developers who are going to be using the code you write, the algorithms and data structures that you write, to make life easier for them. And so we're going to do some short code demos just to show you code that then you can use as the users that Alistair as the developer has pre-prepared in order to kind of hide away some of these details and make life a little bit easier. So this is a file that you will use probably for a good chunk of the rest of semester, and it's called listops.c. And all it is we have wrapped up very nicely for you a lot of these functions. And you'll see in this case, instead of tail, we've used the terminology here foot. The terminology is not super standardized, but either foot or tail are both appropriate. So head or foot if you are a human, and maybe head and tail if you are a dog. So in this version, we have a few different functions that we didn't have previously. So we have make empty list, which is going to allocate a list T structure. And what is our list T structure? It just contains two nodes in it. It contains a head node and a foot node. And you'll notice here that we've also used typedef so that we can directly go to using a list underscore T instead of having to type out struct list every time. So this is perfectly valid C code to just declare struct list, but then every time we want to use the type, we'd have to write both words, both struct and list. And if we use a typedef, then whenever we refer to this type, we can just do list_t without having to write the word struct. So make empty list is not going to take any arguments, but what it will do is it will malloc a structure that contains 2 pointers. So it will create a new structure, it will tell the program, save some memory, and in this chunk of memory, we're going to put 2 pointers. There will be a head pointer and a foot pointer. Then assert that the malloc succeeded, but because we haven't actually put anything in the list yet, the head pointer and the foot pointer should just be set to 0, should be set to null pointers. And then return the list to the user. IsEmptyList is very simple. First, assert that the list itself exists, and then we need to know, once the list structure exists, is there anything in it? So there is a difference between the list structure existing and it actually having some contents. So you can have set aside the memory for the 2 pointers for the head and footer without actually having put anything there yet. And so what this is checking is, firstly, have you set aside that memory? Because if you try and check the head and the footer and you haven't even set aside the memory, you'll get a seg fault. But then all it does is check, is that head pointer actually null? Free list is very similar to what we did before. So first check if the list itself exists. If the list itself exists, start at the head, and as you go through, go from item to item, like exactly as we did before. Keep track of the one you just visited, move to the next one, free the old one. Move to the next one, free the old one. Move to the next one, free the old one, until you get to the end of the list. Then we have our inserted head, inserted foot, get head, which is just going to return to the user the data at the start. So access the list structure, within the list structure, access the head pointer, and within the head pointer, whatever is at the head, access its data. From here on in the semester, you're going to be allowed to use listops.c in your own code. We'll show you how to include that. And then you can use this as a set of library functions that will enable you to build and use listops without having to write your own linked list code. This does not mean you're free to ignore your own understanding of it, because we might say, well, what are some changes that we could make to the linked list that would make things more efficient or make things different? But this at least is a start. Okay, now let's look at an example of actually using listops.c. In this case, we're going to use the include preprocessor directive. And remember, a preprocessor directive is just one of these hash words, so like hash define, hash include, or pounds is what the symbol's actually called. So we're going to include all of listops.c, and then we can do something similar. Make an empty list, insert it head, insert it head, insert it foot. The only thing to note here is we do still have to assign the outcome of these functions to list so that we update it appropriately. And at the end, we can just free the list. So this is all you need to use a linked list, but to understand it, again, is a little more complicated. So summing this act of our class up a little bit, we've seen that you can make a list using multiple different concrete data structures. You can make a list using different concrete underlying data structures. You could use a linked list to make it, or you could use an array to make it. But the properties we get, the runtimes that we get, are going to differ. And we see in this table, for example, that to access the kth element in a list that is backed by an array is only O of 1. If you want to find the ith element in the list or the kth element in the list, just jump to array index k. If you want to do that with a list that is built using a linked list underlying it, that's going to take longer. If you want to get to the kth element, you've got to start at the head and go 1, 2, 3, 4, 5, follow the links until you get to number k. So that doesn't seem so good until we remember that for our queue that we wanted to build, where what we really cared about was adding people to the front and the back and removing someone from the front, this was much more efficient. Then we could do O of 1 additions to the front instead of the O of n addition that we needed to do previously to put something in first place. Or to remove something from first place, we can do that in O of 1, whereas in the old array version, to remove something from the front meant copying everything over one more slot to the front. Here we had our engineering reality check where we needed to match our mallocs and our frees, and we found that we could actually use some tools to do this. Now, our tools are really grouped into two different categories. So our first set of tools are actually built into the compiler, but you can also get additional tools that do them, and these are called static analysis tools. And these are tools that don't require you to actually run your code to get insights about them. So for example, if you're using VS Code or another integrated development editor or integrated development environment, what you'll sometimes see is you'll see, oh, a squiggly line under a line of code you've written, that's telling you there's an error. That's an example of static analysis. It doesn't need to run your code, but can still structurally look at it and see what issues might be there. And there are a whole bunch of tools in this category, and they're very effective, and we use them all the time. But along with our static analysis tools, we also used Valgrind in our example to do dynamic analysis. And this is to gain insights about our code by having our tool run over our program while that program is running. And this allowed us to profile our program and find memory leaks by instrumenting it. So just like a doctor attaches instruments to a human, like imagine you're doing a sleep study and they attach things to your head, this is just like doing the same thing for a running program. So you can catch some problems just by inspecting the patient and without actually attaching any probes. And then you can also instrument your program, instrument your code, run dynamic analysis tools to get further insights. And this was really useful for finding our memory leaks. Here I have a file called bad.c where I have tried to include as many bad bugs as I could. And there are a whole variety of them. And this is actually a really good program to download because it will help you spot the types of errors that you could make in your own code. So at the start of bad.c, I have a memory leak example where I have mallocked 10 characters and then only by the end of the program, I've not freed it. I have a use after free example where I have created a pointer, freed it, and then attempted to use the memory after I've already freed it. I have an example where I have made an array of size 5 and accidentally tried to access array index 5, even though for 5 elements they go from 0 to 4. And then I have an integer overflow example where I've tried to add 1 to an integer that's already at the maximum size. And so our task now is to see how many of these bugs we can find. And one of the tools that I'm going to use to do this is a dynamic analysis tool that is built into our compiler called a sanitizer. Now, Clang, one of the two compilers that we've shown you in this class, has particularly powerful sanitizers. So we're going to run this interesting looking syntax and see what it tells us about bad.c. So the first thing it does is give us a warning, which we will ignore from now. And now I'm going to run bad. Ooh, and this looks funny. This is something we haven't seen before. So it says address sanitizer heap use after free on address blah, blah, blah. What we can see here is that it has found the heap use after free that we did over here, use after free example, where we use the pointer after already having freed it. It also found, and those were all the ones that found. Then we could use Valgrind on bad. Let's do Valgrind. Oh, and this is not going to work because I will need to compile it first without address sanitizer for Valgrind to work. And now it's going to report that there were 3 allocations and 2 frees, so Valgrind was another tool that enabled us to pick that one up. One thing that is interesting to note here is the address sanitizer performed a little differently to Valgrind. The big difference was that Valgrind expected a compiled program that was compiled normally in order to run an instrument, whereas the address sanitizer was part of the compiler, and what it actually did was the compiler would build into the program itself this instrumentation. So instead of Valgrind running over a normal program, Clang with the address sanitizer would actually create a special version of the program that had this instrumentation, that had this address sanitizer. So let's try some other ones that are built into Clang. fsanitize equals integer. So now let's run bad. Oh, there we go. It picked up on our integer overflow. Signed integer overflow, this +1 cannot be represented in type int. So that's pretty good. It picked up on that. Now let's see if there's another sanitizer we can use. Oh, undefined is the other one. Thank you. And I'm not sure we have anything undefined in here. Oh, there we go. Thank you very much, Oscar. Yes, undefined is another sanitizer that exists. And when we run it with undefined, it will say index 5 out of bounds for type int. Now, one of the challenges with the sanitizers is a number of them are mutually exclusive, so you can only compile your program with certain combinations of sanitizers, so you might want to run your program a bunch of different times with a bunch of different dynamic analysis tools to catch all of these different bugs. I will say as a student, this is potentially the most powerful underused technique to find bugs in your code. When you get the why isn't this working, I think I've done everything right. Instead of staring at the code for hours, try running some of these sanitizers. It may just point out some of these bugs. And these bugs, although you don't always know that the reason your program isn't working is this specific bug, it can often be the case that 2 things that are seemingly unrelated are actually connected. One reason in particular that can happen is because a lot of these bugs involve memory corruption, where you think you have written to a variable, but actually you've written to another chunk of the computer's memory, and that other chunk of the computer's memory might be used somewhere else in your program. So when you run that other part of the program, it might look like your memory is behaving weirdly, like that variable is behaving weirdly, but that might only be because some other part of your program has accidentally overwritten. I also have an example up here of using the Mac OS version of the tool, so that's also good to try out. If you're on an M series Mac, there is a branch of Valgrind that you can use to actually get the Valgrind functionality, but it's relatively experimental. And I don't think I've gotten it working yet, not that I've tried super hard, but historically this has been the tool to use. Oh, there we are. Yeah, so these were a few alternatives for finding memory bugs in your code. But what's the real answer that I recommend to people who come to me with these kinds of problems in actual software development companies? The answer is not to use C, where you can avoid it, and to use languages that have been designed to hide some of these elements from the developer. So Python, it is possible to run into memory allocation errors, but it's pretty rare. And the reason is because Python has been designed to hide a lot of these details away. Now, why don't we then just use Python for everything? Well, Python is very, very slow in comparison to C. So there are a whole bunch of competing languages that are aimed to do what C does pretty well, but do it without the foot guns, which is the term of art that programmers use to refer to program design features that allow you to metaphorically shoot yourself in the foot while programming. So a language like Rust is quite popular among people looking to get some of the same power as C, some of the same expressivity as C, but without the foot guns. So our overall story here was that we had multiple representations of our abstract queue. And our queue in this sense is what we'd call an abstract data type. There's no a linked list is not a queue. What a queue is it's an abstract idea that we can have about the way that something should behave. Really, a queue works in terms of first in, first out. So the first person arrives should be the first person to leave, and the last person to arrive should be the last person to leave. That's really what a queue is. Whether you build it with an array or you build it with a linked list, it's still a queue. We don't want users to have to worry about most of the time how we're actually building the queue. We just want them to be able to use the insert at front, remove, insert at end, remove from front. These are really the two key operations of our queue. Another way of saying that is all our users care about is push, pop, insert, search, and delete in for our array and for our linked list. And of these, if we're defining a queue, which of these do we probably want? We want our remove from the front, add to back, and then is empty is also a useful one. And that's pretty much it. That's our queue. So lists, stacks, and queues, and we've talked about stacks a little in this class, are all examples of abstract data types. And the idea of a queue is to abstract away the order of access from the order of arrival. So when you how you access it should not depend on when the thing arrived. Now, the other thing that we've also been doing is abstracting away the representation from the use. So the representation in this case was, do we use an array or do we use a linked list? We didn't actually want the person running listops, like you import listops into your code, you don't want to have to know whether it's actually using a linked list or whether it's using an array to get its work done. All you want to know is what operations does it provide and what are the behaviors that I can expect as a result. So this is one of the core ideas of the whole class, is this notion that you can have abstract data structures which are implemented in multiple different ways under the hood. And how they're implemented after the hood affects performance, but it shouldn't impact the range of operations available to the user. So we can abstract over how data is stored, whether it is stored in a linked list or stored in an array. But can we also abstract over what kind of data is stored, whether it's an int, whether it's a float, whether it's a string? Yes, and we've already seen some of this with our type defs, where we've created alias types that allow us to quickly swap out whether we are sorting over a list of floats, whether we're sorting over a list of strings. What we care about is the ability to swap this in and out easily, again, to make life easier for developers. In programming, we call this, and in computer science, we call this polymorphism, from the Greek poly meaning many and morphism meaning types. And so what this essentially means is designing your code, designing your functions, designing your programs in a way such that the same code can be reused whether you are performing the operation over students, or whether you are performing it over strings, or whether you are performing it over floats, whatever it happens to be, the algorithm should stay consistent and support whatever type, data type, that the user wants to use your algorithm for. One fun analogy that I like to use for this is a vending machine. It doesn't matter whether you want to buy a drink or a chocolate or a candy. The interface provided to the user is the same. You don't have to push separate sorts of buttons and access the machine a different sort of way, depending on whether it's a round thing or a chunky thing or a crispy thing. The machine works the same way. And this is what polymorphism is all about. So generic sorting algorithms need one thing from the user. They need a way to compare two items. Because in order for us to tell which thing comes first and which thing comes next, we need some kind of way to define that. So for example, for students, you might say compare them by age, or you might say compare them by grade, or you might compare them by height. And so in order to sort them, we need to have a clearly defined notion of what the ordering actually is. And over the next little while, we'll see how this comes in handy for more than just pure sorting, but for some of our other data structures. Defining the notion of an ordering becomes really important for us to be able to run efficient algorithms. So just like I said before, we can sort numbers, we can sort precedents, we can sort words, but in order to do so, we need to define what it means to sort over those items, or more concretely, what it means to order those items. So we could actually look this up on Wikipedia, which is what I did 5 years ago when I was first preparing these slides. What is an order? And we get this beautiful mathematical definition about what an order is. I would encourage you to go and read up this interesting stuff, but we're computer scientists, so we're going to throw away a lot of that. For us, we're really going to ask this question. Is A the same as B in terms of our ordering? Should they be equivalent in our ordering? Is A bigger than B, or is A smaller than B? And this is the only question we need practically to actually define our sorting. And indeed, in your assignment, we showed you an example of a function which can be used polymorphically, which is designed polymorphically, and all it needs to function is a definition of what this ordering is. And to do this, and in order to actually give it this information about the ordering, what we defined was a comparison function, a function that captures the notion of our prior slide about which is bigger, which is smaller, which is the same. So in order to use qsort, in order to use the sorting function, you provide a comparison function. The comparison function implicitly defines the total ordering, and the way it defines the total ordering is for any pair of items, it tells you which one is bigger, which one is smaller. Qsort in this way is our bridge from generic data structures to ordered data structures, because right now we have our array, we have our linked list, they don't have an inherent order to them. As an abstract data type, an array and a linked list don't have an ordering. No item is before or after the other, except in the sense that it might take you longer to access one in a different position. But just because it's in a different position doesn't mean that they're actually ordered that way. That's just how they're stored. And how something is stored is different from, are they ordered in like sorted order or unsorted order? And qsort is going to be one of the tools that we can use to polymorphically sort things. So if we want to use qsort, we can look up the manual with the man pages, as we showed earlier in semester. And if we were to zoom in a little, we could see that all it really needs is this compare function. And it actually defines for us what this compare function looks like. It takes in 2 pointers, pointer A and a pointer B, and then just returns to the user which is the larger. Now we have a new challenger approaching. So a queue is going to answer for us who is next in the order. But our ticket system for our Taylor Swift tickets that we've been talking about all along is really going to need to be a little bit more sophisticated than that. Let's say you're trying to figure out seating arrangements later on. You're going to need to know who is in which seat. So for example, who bought ticket number 42? Now, tickets imply some kind of ordering because you might have tickets that are sold earlier versus tickets that are sold later. And linked lists are going to be a pretty bad way to find who has the 42nd ticket because you're going to need to go next, check through all of them. There's no notion of ordering in a linked list inherently. But we've seen some how linked lists could be effective data structures. We've seen already how by using certain data structures, we can improve the performance of our algorithms. And so what we want to do now is to think, okay, if linked lists are kind of like our analog to linear search, going through everything one by one, we know that there's a better way to search through things when there's an ordering. It says up there. What is it? It's binary search. So if we have a a one-dimensional structure that's like our one-dimensional linear search, and our binary search could go two directions, that implies that maybe there is a two-dimensional version of a linked list that we could use to try and capture the same advantage that we got from moving to binary search, just with our data structure version. And this is where we start to see the really interesting parallel between the design of the data structures and the design of the algorithms. So sometimes you can take an improvement that you made algorithmically and use it to design a data structure that has that kind of algorithmic idea built into it. And this is where we introduce binary trees and eventually binary search trees, which will allow us to capture some of that binary search behavior. So let's just start with a basic binary tree. So I gathered a few of my friends to help illustrate the point. These are all my ape friends, and I've arranged them in a two-dimensional structure that we're going to call a tree. And in this case, in particular, it's a binary tree because every node has two other places it can go. It can go to the left or it can go to the right, and we need some terminology here. So we're going to call the root of the tree. Now I know trees normally have their roots in the ground, but in computer science we're a little reversed. We have our roots at the top. So our root at the tree is Naruto at the top, over there. And then each node is going to have what we call children. So all the nodes that spring directly forth from a single node are called its children. So for example, Naruto has two children, Rafiki and King Kong. But Naruto also has a lot of descendants. And so descendants refer to all the children, and all the children's children, and all the children's children, and all the children's children up until the end. And on top of this, we have one more useful word that I want you to know, which is leaf. So a leaf is a node that has no children. So in this case, King Louis has no children. King Louis is a leaf. Donkey Kong has no children, so Donkey Kong is a leaf. And that's what we've got there. Now, all of these monkeys are coming to see Taylor Swift with me. I thought they would enjoy it far more than Lily, who evidently is not a fan. And so I've allocated them all different ticket numbers. But now we've got our problem that we had before. The ticketing agent, the stadium, wants to figure out who has which ticket number, who has the largest ticket number, who has the smallest ticket number. And that's going to be a little tricky with the structure as we have designed it here. So let's think back to our linked list version. And what we've done is very, very similar. Instead of having one pointer out from every node, we now just have two. We have the data that's still there, and we have a pointer to the left child and a pointer to the right child. So now let's see how we'd actually use this data structure to find the monkey with the highest seat number. Okay, here we go. Starting with Naruto. Let's check his left child. Okay, Rafiki. Let's keep track of the highest seat number we've seen so far. It's 33. 27 is not higher than 33. Now let's go. 27 has a left child. That's King Louis. King Louis, 14 is not higher. Okay. And now we're stuck at the bottom of the tree. So what can we do? I don't think I've seen the highest seat number yet. So what should I do at this point? I've reached the bottom of the tree. What was that, Caitlin? Go back up. So to go back up, let me keep track of what the parent was. Okay, I'll go back to the parent. The parent doesn't have a right child, so we can't go that direction. I guess we have to, what do we do again? Go up again. Okay, we're back at Rafiki. Rafiki doesn't have a left child, so what do we do? Up again. Okay, we're back at Naruto. Okay, now I guess we can go to the right side, and the highest we've seen so far is still 33. We're at King Kong, but 14 still has a child. Okay, let's visit the child. That is, Apu. I forgot I keep forgetting all these monkey names. Okay, Apu has two children, so let's visit Mojo Jojo. Mojo Jojo has seat number 40. Okay, that's higher than 33, so let's remember that. Mojo Jojo doesn't have a left child, but has a right child, Donkey Kong. Donkey Kong, King Kong, this is getting very confusing. Donkey Kong doesn't have any children, so we can't go there. So what do? We backtrack again. Mojo Jojo doesn't have a left child. We've already visited the right child. Back again. Apu has a right child. That's, I've forgotten, what's her name again? Nala? And Nala doesn't have any children. Not Nala. I'll have to go and check my old slide. There are too many monkeys. Doesn't have any other children. We've now been through all the elements. This took us a long time. This wasn't any better than linear search. Kala, that's right. So this was not better than linear search. And in fact, it might have even been worse because we revisited things that we'd already looked at a bunch. So that gave us O of 2n time in the worst case. We're just O(n) of time. And this wasn't the binary search improvement that we had hoped for. So a little sad. But binary search needed something special to work. What was it? Yeah, it needed sorting. And needed really an ordering of things to work. And so our idea here is find an ordering of the elements that's fast to construct in a data structure, then figure out a way to map that to our tree. So if we can build a data structure that contains this kind of sorting notion, then we can do search much faster. Now you could say, why not just use an array and then sort the array? That isn't a bad idea, but we can probably do a bit better along a number of ways by building this notion into our structure such that when we insert or remove elements, we can do better than our sorted array where insertion and removal was expensive. So like the advantage that we got for our queue with our linked list, where insertion became much more efficient, even though still going to a particular index was slow, maybe we can do the same thing with our tree structure, which if we modify it, we can get both the fast behavior for search, but also fast behavior when we need to add and remove things. And this is where binary search trees come in. And so on top of our basic property of every node can have at most 2 children, and those children have to be unique, so you can't point a child back to its parent. A child's child is not its parent. That would be invalid. So we'll add, and that'd be a very bad idea. Back to the Future style. So we need an additional rule to make this work. And in this case, our rule is going to be as follows. This is the convention that we will make everything on the right subtree bigger than the parent, and the parent is going to be bigger than everything on the left subtree. Now, I also did have to account for the case that there are elements equal to the parent, and so I'm just going to put those in the right subtree. Now, of course, this is just a convention. You could reverse it such that everything bigger is on the left and everything smaller is on the right, but by convention, we put the big things on the right. So let's just imagine that we've already built one of these binary search trees, and we'll get to how they're constructed, how addition and removal works, but let's just imagine for now that we've already built it up. And so let's first look to observe that our property is actually correct here. We have from Naruto, who has seat number 20, everything on Naruto's right has a larger seat number, and everything on Naruto's left has a lower seat number. Now let's look at Rafiki. Everything on Rafiki's right is similarly bigger than Rafiki, and everything on Rafiki's left is similarly smaller than Rafiki. And so now let's try do our search for the monkey with the highest seat again. Let's try run this again. Okay, starting at Naruto. You've got three directions to go. Okay, let's say I'm trying to find the largest monkey. I know that smaller is on the left, bigger is on the right, so which direction should I go?
Right.
Right. Okay, so which monkey does that take me to? Do you remember all the monkey names?
No, I don't.
Okay, we'll go right to Rafiki. Okay, now we want to find the largest monkey, so should I go right or left?
Right again.
Right again. And now I want to still find the largest monkey. Should I go right or left?
We stay there because there's no right node.
There's no right, which means we have found the largest monkey. So this was much, much faster than it was before. In fact, it only took us 3 steps when previously with our unordered binary tree, it took us we had to visit all the nodes in order to find it. So this already looks like an improvement. What is the big O time of this? And this is actually a little tricky. Do you have a sense of what it might be?
Maybe log n?
That's not a bad idea. You're kind of on the right track. So that's ideally what we'd aim for, and it would be log n if we were guaranteed that the tree is going to be what we'd call balanced. And what this means is that there are equal number of nodes on like both halves of the tree, and the tree like looks like a fully filled out tree. We'll talk a bit more about that later. But the problem here is that we don't necessarily know how our tree is going to be arranged, which makes figuring out the big O behavior really tricky. Because it could be that we would have had to keep going right. Our tree could have actually been a stick. Just one leaf, one node connected to another node, connected to another node, connected to another node, in which case it really just looks like a linked list because no one has a left child. And so that would kind of be O of n. So for now, what we're going to say is that the worst case runtime is going to be O of h, where h is the height of the tree. And the height of the tree is the maximum distance, the maximum number of steps you could take to get far away from the root. So in this case, the maximum number of steps that we could do is how much? So we go 1 step, 1 step, 1 step, 1 step. That would involve looking at 5 nodes. So we'll say this tree has a height of 5. And this is why we have to kind of shift our thinking a little bit about what a big O behavior is. But don't worry, we'll get to a point where you can more confidently talk about what H might actually be. So, as you said before, this looks pretty similar to log n, and this is going to be our average case under a particular set of assumptions about how the tree is constructed. So for an average tree with average items that are distributed in an average way, and we're not going to be super precise about that for now, we are going to get this log n behavior. So your intuition was totally on the money there. So that was a great job. And we can use the same technique not only to find the largest value in our tree, but to find any value. The only problem is when we get this pathological stick behavior and our tree is just one long linked list. So for n items in a stick, we'll get a height of n. So we have worst case O of n, which is not great. So part of the challenge in the binary search research literature is making sure, and the data structures literature in more advanced classes, is trying to make sure that we get an optimal binary search tree. And while we have solved this to some extent on how to do algorithms that give us really nicely constructed binary search trees, there are still plenty of cases for which there are open problems. Unfortunately, given the scope of this class, we're not going to be able to show you how to build the balanced binary search trees. You'll get to that in second year, hopefully, unless we have lots of extra time and people are super interested. Okay, so for the next couple of minutes, it's going to be your turn. I want you to sketch out 2 algorithms for search using this data structure. So see if you can write out the algorithm yourself, pick either iterative or recursive, and write out the function that will allow us to search for an arbitrary value inside the tree. And I will give you 5 minutes for this. Okay, coming back, let's look at how we might actually go about doing this. It's pretty similar to the list code that we've been doing before. So this is a search function for a binary search tree. It's going to take as input a node, and in this case, I'm going to have hard-coded in the value 42 that I'm looking for. You could add that in as a parameter to the search function easily enough. So just like we did with the linked list, we have to keep track of what the current item that we are looking at is. And so I'm going to take in the root and create a pointer to the root called p. And then first I check that p exists. And then I'm going to make sure that the current item that I'm looking at isn't the one that contains the data I need. If it doesn't contain the data I need, check its check if what I'm looking for, in this case 42, should be on the right side or the left side, and then repeat this process. So because we know at each step that we don't need to search both directions, we'll only need to search one of the directions, it's just a matter of making the decision about which direction to search. So we know that if the current item that we're looking at is bigger than 42, we should search only on the smaller side. So set P, our new current one, to be the left child. Otherwise, set it to be the right child. And here is the recursive version, which is really, really nice and small. You shouldn't actually write your code quite as tersely as this, but it's very nice for illustrative purposes for this kind of class exercise. So if the current thing you're looking at is 42, return it. Otherwise, if it's bigger, run the recursive version on the right. If it's smaller, do the recursive version on the left. So now all we need to do, now that we know search, which is the whole point of this, we just need to deal with creation and deletion, or insertion and deletion. So insertion, I'm going to show you both of these algorithms in very much pseudocode form, and then maybe Hanja next week will go over the actual C code for you, which introduces some interesting C concepts. But for now, we're going to look at this kind of pseudo C version, just like we did before. So this is the recursive version of insert on the binary tree. And in this case, I'm not including some of the extra minor checks, so I'm not checking if the root exists. We're assuming that for this purposes here. So first, we have two branches. Is x bigger or is x smaller? Within those branches, we want to check if the item we're looking at already has an existing left child or a right child. If it already has an existing left child or right child, we're going to need to deal with that. And if it doesn't, we can just plop the new item there. So that's what we're going to do on these else branches. If there is no pre-existing child there, just plop it on at that spot. If there is an existing child, we're going to need to do this recursively for that child. We're going to need to look at that child, see, oh, is it bigger? Is it smaller? Should it be plopped? Should it not be plopped? Okay, so let's imagine we're trying to insert 28 into this binary search tree. Is it bigger than 20? Does 20 have a right child? Okay. What about, now we do recursively on the 33. Is 28 bigger than 33? No. Does 33 already have a left child? Yes. Okay, so let's run this recursively on the left child. Is 28 bigger than 37? So is 28 bigger than 27? It is bigger. Does 27 already have a right child? No, so we can just plop it in there. Okay, now deletion. Deletion is where things actually get a little tricky. So how does deletion work? Well, here's the pseudocode for it. And again, this code is not going to work if we're trying to delete the root. We'll need to go over that separately, and that would make the code a little harder to do. So the first thing you're going to do is find the parent of the node you want to delete. So every child has a parent. I don't think I introduced that terminology before, but it's straightforward. If you are a child, the node that is one higher up of you is your parent. So let's imagine we have a function that just finds the parent and store that in P. Then create a temporary variable called onLeft and set it to be equal to if you are on the left side of your parent or not. So find your parent and figure out if you are your parent's left child. Is anyone here their parent's left child? I've left my parents, so maybe that makes me their left child. Okay, figure out if you are on the left of your parent. The next thing you want to do is determine if you yourself have children. If you don't have children, this is pretty easy because you can just be removed without impacting anything further down in the tree. You don't have any descendants, and so you can just be deleted. And this is computer scientists' best argument for having children. If you don't have any children, you can just be deleted. So if you don't have any children and you're on the left, set your parent's left child to null and just free your own memory. Otherwise, if you're not on the left, then that means you're on the right, and we're in the branch where you don't have any children, so set your parent's right pointer to null. This was the case where you are your parent's child, figure out which side, find your parent, figure out which side of them you're on. If you don't have any children yourself, you can just be safely removed. That's the easy case. Okay, so here is an example of that case. We want to delete 21. 21 doesn't have any children. Find the parent, 22, figure out which side 21 is on. 21 is on the left. It can just be removed. Nice and easy. Okay, now we get to the slightly harder case. So let's imagine that you only have one child. So in this case, you don't have a right child. So if you're on the left of your parent, set your parent's left child to be your left child, because you're just deleting yourself, your child still wants to stick around, and so attach that child to your parent on the left, because you were on the left too. Otherwise, do that for the right. Make the parent's right side your left child. This is where you have a left child. You have to figure out which side of your parent to put it on. If you were on your parent's left side, put your left child on your parent's left side. If you were on your parent's right side, put your left child on the parent's right side. Let's do an example to make that clear. We're trying to delete 22. Find 22's parent, which was 27. We're on 27's left side. 22 has a left child, so we're going to attach our left child, 21, to our parent, 27. So we're going to attach Donkey Kong to Sun Wukong's left side. Makes sense. When you draw it out visually, it's quite clear. The tricky thing is more figuring out all the different cases in the code, because now for every node, we could either have no children, we could have a left child, we could have a right child, we could be on our parent's left, we could be on our parent's right, and our code needs to account for all of those combinations. Okay, so we have the opposite, where now if we only have a right child, we do the same thing, which I'm not going to display because that's just the exact same as the other, just mirror image. And now we have the actually tricky case, where you have two children, and those children potentially have their own children, and we need to figure out how to rearrange the tree such that the binary search tree property stays, because we can't just put a random one there, because then we might mess up the ordering of bigger and smaller. So this is what we have now. We have to find the successor, your successor, so who is next in line up from you, and that is going to happen on the right side. So we want to find the next biggest one after you, and we know the next biggest one must be on your right because everything on the left is smaller. So the one that's bigger must be on the right-hand side. So find the smallest value that's on your right. So that means out of all the things that are bigger than you, find the smallest one of that set, and that is the next one in the order as compared to you. So find that next one, and then swap yourself in the position on the tree with that next one, and then you can delete yourself. So here's the example. We want to delete 33. Out of everything in 33's descendants, the next one along is 34. In order to find it, we look at the tree containing, the subtree containing 34 and 40, And out of those, 34 is the smallest. That's our find minimum. And we know how to find minimum and find maximum. We're not going to repeat that here. So what we do is we find 34, which is the successor. We swap 34 and 33. And now we swap 34 and 33. And now we can delete 33. And because 33 only has one child, this is much easier. But notice in the code, we actually called the delete function again. So this is a recursive call to delete because we also have to account for the case where what if the successor also had 2 children? So if the successor had 2 children, we're going to need to find the successor's successor, swap the successor's successor with the one that's now in this place, and then run the delete process again. And by doing this recursively, we're going to just swap things up to the point where our binary search tree property stays intact regardless of the deletions. So in the next lecture, we're going to actually look at how to implement these. But for now, I want to take us out with some of the really interesting ideas that we get as a result of this. So just like we could implement stacks, queues, and lists with arrays or with linked lists, we can also add binary search trees into our repertoire of concrete things that we can implement other ideas with. One of the abstract data types that we can actually implement using a binary search tree is a dictionary. And the way a dictionary is going to work is, let's say we have our apes, and our apes have a seat number and a name, and we want to find the name that corresponds to a given seat number. We're going to call the seat number, in this case, the key. It's the thing that we're looking up by, and the value is the name of the ape. That's the thing we want to know at the end of the day, and the key is going to be our identifier that we use to look for that. Another example that's very familiar to all of you is all of you have a key, which is your student ID, and your email address or your login name or your personal details are the values associated with that key. And a binary search tree is one possible way of implementing a dictionary. And the crucial elements, the crucial functions that we need for this abstract data type is we're going to want insertion and deletion, and we're going to want to be able to search by key. So if I give you a given seat number or if I give you a given student ID, can you give me back the identity of the individual associated with that or the data associated with that? And so we could implement a dictionary with a binary search tree in multiple ways. We could use an unsorted array to do it. We could use a sorted array. We could use a linked list. We could use a binary search tree. And this gives us different algorithmic properties. If we use an unsorted array, searching, if we want to find a given item in the array, it's going to be O of n, just like it always has been. But to insert, we can just dump the new item on the end. That's O of 1. For a sorted array, our insertion is going to be O of n because we need to find the right place to put it in. And even once we find the right place to put it in, then we need to shift everything along to make room for it. So insertion is O of n. But search, we can do binary search, so that's log n. Remember, binary search is log n because we figure out which half it should be in. For linked lists, we have kind of the opposite behavior. We have insertion is really fast, but again, we have this kind of unsorted array property where search is going to be O of n because we have to go through the entire linked list. For a binary search tree, if we have a stick, then we're going to end up with O of n insertion and search. But we've already said we can probably get our binary search trees to an average case where we get log n insertion and log n search because we're doing, because it's going to be proportional to the height of the tree to how many steps down we have to go. And this is going to show us the big idea at play here, which is we can have one kind of task that we want to do. Our task is to design a data structure that kind of performs this role for the user. And we can implement it in lots of ways and get different trade-offs by this. And in the subsequent lecture, you're both going to see how to implement a binary search tree, but also possibly another data structure that we can use to get a different set of performance trade-offs that a lot of people are really going to like for the dictionaries. But for now, given that we are at the end of the lecture, I think our tickets are distributed for today, And so we only have one thing left to do. With a bit of a shake it off, the main thing you need to remember from today is this core idea. Representations are going to change the algorithms under the hood. They're going to change the efficiency, but we can use abstraction to hide it from the user and make things much, much easier to use and much more efficient. So with that, who has my Taylor Swift tickets? Thank you very much, everyone, and I will see you soon.